So we can look at the energy changes that occur when a solution forms. So we can think of a solution forming in 3 steps. So the first thing is we have to separate the solute particles, because whatever substance it is, if liquid or a solid or whatever, those solute particles are stuck together. So we have to pull those apart from each other. That's going to require energy. So that's going to be a positive energy change. It's an endothermic process. Then we also have to separate the solvent particles so that the solute particles can get in, right? Make room for them. That's also endothermic. So now we've put in energy to separate the solute particles. We've put in energy to separate the solvent particles. When we allow the solute and the solvent to mix with each other, now we're gaining interactions, and so that's going to release energy. Does that make sense? So this is going to be exothermic. It's going to release energy. Now the overall energy change is going to depend on the magnitude of these. We've got 2 positives and 1 negative, and whether it adds up to positive or negative depends on how big those numbers are. So the enthalpy of solution is the sum of the changes in enthalpy for each step, separating the particles and then bringing them together. The overall sign is going to depend on the magnitudes. So a solution forming can be exothermic, it can release energy, or it can be endothermic and absorb energy. So what are we looking at here? We're looking at formation of a solution. So here we've got a solvent and the solute. And here the particles are aggregated. They're connected with each other, right? And so to separate the solute particles, we have to put in energy. That's delta H for the solute, separating those. And then we have to take the solvent particles and separate those. We put more energy in, delta H solvent. Now we've got those separated particles and we allow them to come together. That's going to release energy. We're calling that delta H mix for the mixing. So the overall process for this one is exothermic because the energy released when those mixed was less than the energy we had to put in to separate the solute and the solvent. Does that make sense? We can also have an endothermic solution forming, separating the solute particles, separating the solvent particles, and then allowing them to come together, releasing energy. But here the amount of energy released is less than what we had to put in to separate them. And so this is a net endothermic process. As this solution forms, it absorbs energy from the surroundings. Any questions? We deal a lot with aqueous solutions of ionic compounds. And so for those, we can take delta H solvent, that's separating the water molecules from each other, and delta H mixing, that's the energy released as the solute interacts with the water molecules. We can put those 2 terms together and call that heat of hydration. So you've got your solute particles and you're allowing them to mix with the solvent. That's measured as an enthalpy change when 1 mole of gaseous solute ions is dissolved in water. It's always going to be largely negative. So exothermic. For the solute, that amount of energy needed to separate the solute particles for an ionic compound is the same amount of energy released when that compound formed. It's the lattice energy. But instead of releasing energy, we have to put the energy back in to separate the particles. So delta H solute is equal in magnitude to the lattice energy. It's just opposite in sign. So the enthalpy change for the solution is the sum of the energy needed to separate the solute particles energy needed to separate the solvent particles, and the energy released when you mix them. So these two are combined into one term called heat of hydration, always negative, and this one, heat of delta H solute, that's always going to be positive. Okay, so here's potassium fluoride. To separate the potassium and fluoride ions, you have to put in energy, that's delta H solute. That is equivalent to the lattice energy, but opposite in sign, because you have to put it in to break the things apart. Lattice energy is the energy released when these particles come together, so it's going the opposite direction. So you've separated the particles, and now the heat of hydration is what happens when those separated particles mix with water. So here the heat of hydration is minus 819. The lattice energy was 821. And so the overall difference is that you have to put in 2 kilojoules per mole of energy for this solution to form. It's an endothermic process forming this solution. It takes in energy from the surroundings. And so this solution will feel cold as it forms. Other solutions are exothermic when they form, and they'll get hot. You can mix 2 things together and they just get hot. There's no burner involved. It just got hot all by itself because it's releasing energy that was stored. Any questions?